Swayam Prabha. Digital India. Educated India.
Welcome to lecture number 6 of flow of water through soils. So, in the previous lecture, we have solved Laplace equation, which is theory of continuity for based on the seepage for computing the seepage. In this lecture, we will be looking into the flow net methods. In the previous lecture, we have introduced methods for solving Laplace equation of continuity. So, in this lecture, we will be discussing one of the methods, that is flow net methods and flow net construction, and some example problem. So, in the equation of continuity, when we defined in the previous lecture, for flow in saturated soils, where the fluid has uniform and constant density, the equation of conservation of fluid mass is given here. It is commonly called as continuity equation, and this is for soils which are having permeability, identical permeability in all directions, that is Kx, Ky, Kz is equal to K. So, with this del square phi is equal to 0 in terms of 2-dimensional, 3-dimensional flow considerations, we can write like dou square h by dou x square plus dou square h by dou y square plus dou square h by dou z square is equal to 0. This also can be indicated as del square is equal to 0 as a Laplace equation of continuity. And we mentioned about methods for solving this type of Laplace equations, and then we identified that one of the methods for solving popular methods for solving the Laplace equation of continuity is the flow net method, which is based on the graphical method of construction. So, in this lecture we will be looking into the flow net method details, and then its construction details, and then some example problems for computing seepage. So, the possible methods for solving the Laplace equation are given here in this slide. We are reviewing whatever we have discussed in the previous lecture. So, analytical closed form or series of solution of the partial differential equations. So, quite mathematical and not very general, that is what we have discussed. And another method which is possible for solving the Laplace equation of continuity is the numerical solution methods. Typically, the finite element method or finite difference method are used, very powerful and easy to apply, can deal with heterogeneity, anisotropy conditions, and 2D and 3D conditions. The another third method which is we are going to discuss today is graphical techniques, that is flow net methods, commonly used in engineering practice to solve 2-dimensional problems. So, while introducing this, we also discussed that many flow types like 1-dimensional flow types, 2-dimensional flow, and 3-dimensional flow considerations. So, most of our problems for computing seepages will be adopting the 2-dimensional flow considerations. Basically, the flow net method is for the 2-dimensional flow based on the 2-dimensional flow considerations. That indicates that we assume that the structure is continuing per meter length perpendicular to the plane of the figure under consideration. So, here we have discussed that this flow net is nothing but a family of two lines. One is called a flow line, another one is called equipotential line. And we also said, we discussed that, and we have shown, and we have noted that a partial flow net which is shown here, which has got equipotential lines, different equipotential lines which are shown in yellow color, and this red one which is the flow which is taking place along the flow which is taking place through this. So, they are called flow lines. The space between any two flow lines is called flow channel. and between two equipotential lines there will be a head loss will occur. So, this particular the potential between here and here, the flow is occurring in that direction, then there will be a loss of head. So, the straightforward graphical method to solve two dimensional seepage problems, as what we mentioned earlier, that flow net method is a straightforward graphical method to solve two dimensional seepage problems. So, solutions of Laplace equation consist of two families of orthogonal curves in the xz plane. So, xz plane in the sense x the horizontal distance and z the depth. So, what we are considering is the two dimensional problems under consideration. So, these families of curves make a flow net. So, that is what we have seen, and now when you come to the seepage and flow net solution, the flow net solution is a graphical method of solving the two dimensional Laplace equation. So, in the two dimensional case, this Laplace equation of continuity reduces to dou square h by dou x square plus dou square h by dou z square is equal to 0, because we are considering now xz plane. So, the equation of continuity is now is dou square h by dou x square plus dou square h by dou z square is equal to 0. In case of one dimensional flow, like dou square h by dou x square is equal to 0. So, if the flow is taking place only in along the x direction, then it is called dou square h by dou x square is equal to 0. So, it describes the energy loss associated with the flow through a medium and is used to solve many kinds of problems. So, this particular concept is is used in solving heat transfer and electricity transfer and seepage, that is from electrical transfer from one potential to another potential. Again, the similar concept and similar analogical logic is used to explain this particular theory. So, this flow net solution it basically describes the energy loss associated with the flow through a medium and is used to solve many kinds of flow problems, basically for solving flow problems including those involving the heat, electricity and seepage. So, when you come to the this particular flow net, we said that the two families of curves. So, one is please note that is flow lines, another one is equipotential lines. We will come to these details of definitions later, but consider that one of these equipotential lines, they are represented by potential functions, say phi. Similarly, these flow lines are represented by a stream function or flow function, flow function psi. So, here flow nets are based on the two mathematical functions, potential function phi and flow or stream function psi. So, consider a function phi xz such that dou phi by dou x is equal to Vx, that is the velocity in the x direction, is equal to minus k dou h by dou x. This is negative because the head loss is occurring in the direction of the flow. Head loss is occurring in the direction of flow. So, similarly, dou phi by dou z is equal to Vz is equal to minus k dou h by dou z. So, consider a function phi xz such that dou phi by dou x is equal to Vx and dou phi by dou z is equal to Vz. So, what we consider is that this families of curves are represented by functions called psi 1, psi 2, psi 3, psi 4 or phi 1, phi 2, phi 3. So, phi 1, phi 2, phi 3 here this psi 1, psi 2. So, let us consider these flow nets are based on two mathematical functions. One is potential function phi and flow or stream function psi. So, consider a function phi xz such that dou phi by dou x is equal to Vx is equal to minus k dou h by dou x and dou phi by dou z is equal to Vz is equal to minus k dou h by dou z. So, this is negative because the head loss is occurring in the direction of flow. So, in this slide here in this a part of the partial flow net is shown. The red lines indicate streamlines, that is flow lines, and represented by a function called psi 1, psi 2, psi 3, and flow these equipotential lines which are represented by a function called phi 1, phi 2, phi 3. So, the flow is occurring in this direction. The space between any two streamlines or flow line is called flow channel. So, here the distance between two flow lines is A and distance length of the flow line here is B. So, the ratio of A to B is defined as a aspect ratio. ratio of A to B is defined as aspect ratio. So, here if you say phi 1, phi 2, phi 3, as the flow is occurring in this direction, suppose the flow is occurring is here. So, the head loss which is taking place, so the head loss which is occurring between any two adjacent potential lines is also called potential drop. So, in a flow net, number of potential drops will be there from starting point to the ending point where the flow is ending. So, in order to see whether this potential function and stream function, whether they satisfy the Laplace equation of continuity or not, and then also in order to prove whether how we can say that they are orthogonal. So, that also we can try to derive based on the considerations. So, for that consider a function phi x z such that dou phi by dou x is equal to V x is equal to minus k dou h by dou x. Let us indicate this particular equation as A, and dou phi by dou z is equal to V z is equal to minus k dou h by dou z, which is let us indicate this as B. Now, by differentiating equations A and B and substituting in Laplace equation of continuity, for two dimensional flow we have defined that Laplace equations of continuity is dou square h by dou square plus dou square h by dou z square is equal to 0. Substituting equations A and B after differentiating, and if we get dou square phi by dou x square plus dou square phi by dou z square is equal to 0. So, this indicates that the potential function whatever we have considered phi x z satisfies the Laplace equation of continuity. Similarly, here now the seepage which when you integrate say A and B. So, previously we have introduced the A and B. So, that A and B equations are represented here again. Dou pi by dou x is equal to V x is equal to minus k dou h by dou x, dou pi by dou z is equal to V z is equal to minus k dou h by dou z. If you integrate from A, we will get phi x z is equal to minus k h x z plus function of z, and phi x z is equal to minus k h x z plus j x, that is g x is a function of x. So, here from A and B, by integrating this A and B, this is A and this is B, we get this particular equations. So, since x and z can be varied independently, function of z is equal to g x is equal to constant. So, now by simplifying we can write the equation C, which is h x z is equal to minus 1 by k into C minus phi of function of x z, that is phi x z. So, if h x z represents a constant h 1, suppose if h x z at a point x z represents a constant h 1, then the equation C represents a curve in x z plane. So, what we have deduced is that the equation of this potential line, if h x z represents a constant h 1, so for that particular point this equation C represents a curve in a x z plane. So, what we did is that we considered dou phi by dou x is equal to V x is equal to minus k dou h by dou x, and dou phi by dou z is equal to V z is equal to minus k dou h by dou z. So, we try to see whether this potential function fulfills Laplace equation of continuity or not. Then what we did is that after fulfilling that, we tried to obtain whether this potential function line represents the equation, that is the line or not. So, for that what we did is that integrated that A and B equations, and then since because x and z can be varied independently, so we have written that a function of z is equal to g x is equal to constant. So, with that we have written h x z is equal to minus 1 by k C minus phi x z. So, here if the x z represents a constant h 1, then we said that equation C represents a curve in x z plane. So, equipotential line is a curve in the cross section such that phi is constant along the curve. That is that equipotential line is a curve in the drawn which is in the cross section of a particular structure under consideration where the flow is taking place in a two dimensional plane. So, equipotential line is a curve in the cross section such that phi is constant along that curve. That means that the potential will be constant. Suppose if it has got a head h 1, the h 1 will be constant along that particular potential line. So, total head is constant along that equipotential line. That is what it says, that total head is constant along that equipotential line. So, thus the family of curves is similar to the contour lines on the topography. So, if you compare this potential lines, these families of curves of these potential lines, they are analogous to contour lines in a topographical map, but only thing is that except that it is drawn in a vertical section and the lines represent equal heads, not equal elevations. In case of contour lines, it represents equal elevations and it is drawn in a plan, but in this case of potential lines, it is drawn in a section, cross section, and it represents equal heads. So, now having said, now we will try to determine the slope of the potential line. For that, along such contours of equal total head. So, whenever we have the contours of equal total head, we can say that d phi is equal to 0, that is the change in potential difference, potential head between in a particular along particular potential line is 0, that is d phi is equal to 0. So, from the definition of partial differentiation and combining equations dou phi by dou x is equal to Vx and dou phi by dou z is equal to Vz, it gives d phi is equal to dou phi by dou x dx plus dou phi by dou z dz. Now, substituting for dou phi by dou x Vx and dou phi by dou z Vz, we can write d phi is equal to Vx dx plus Vz dz. So, as along an equipotential line d phi is equal to 0, so equating d phi is equal to 0 here, we can write dz by dx of potential line is equal to minus Vx by Vz, that is minus Vx by Vz. So, Vx is the velocity in the x direction and that is where that dz is the depth which is there, and perpendicular to its plane the length is 1 meter. So, the flow area over which that Vx is taking place, that is dz into 1. Similarly, Vz which is erupting out of x in the, that is dx. So, perpendicular to that area is say 1 unit. So, dx into 1 is that area over which the flow is occurring. So, Vz and Vx are the elasticities in the x direction and z direction. So, the slope which is given by dz by dx of the, that is the potential, as minus Vx by Vz. So, dz and dx are the small lengths of the element under consideration. So, what we try to do is that along such contours of equipotential lines. So, we have defined equipotential lines and we said that where the potential is constant in a particular equipotential line, that is total head is constant. So, in that case d phi is equal to 0 on an equipotential line. So, from the definition of partial differentiation and combining equations dou phi by dou x is equal to Vx is equal to dou phi by dou z is equal to Vz, we obtained d phi is equal to Vx dx plus Vz dz. So, along an equipotential line phi is equal to constant. So, d phi is equal to 0. With that, what we did is that we determined a slope of an equipotential line, that is dz by dx is equal to phi, that is potential function is equal to minus Vx by Vz. Similarly, now having seen potential function, let us consider now whether the stream function or a flow function psi satisfies Laplace equation or not. So, for that here consider a function phi xz such that dou psi by dou z is equal to Vx minus k dou h by dou x minus dou psi by dou x is equal to Vz is equal to minus k dou h by dou z. Note that this psi is a inverse of potential function, psi is inverse of potential function. So, consider a function that is stream function psi xz such that dou psi by dou z is equal to Vx is equal to minus k dou h by dou x and minus dou psi by dou x is equal to Vz is equal to minus k dou h by dou z. So, combining equations and substituting in the Laplace equation again, and we get dou square psi by dou x square plus dou square psi by dou z square is equal to 0. So, with that we can also say that the stream function also fulfills the Laplace equation of continuity. So, psi xz also satisfies the Laplace equation, that is what we are saying here. So, that psi xz also satisfies the Laplace equation. So, from the definition of the partial differentiation and combining equations minus dou psi by dou x is equal to Vz and dou psi by dou z is equal to Vx, it gives total differential. If you determine for a psi xz, d psi is equal to dou psi by dou x into dx plus dou psi by dou z into dz. So, we can write now by substituting for minus dou psi by dou x is equal to Vz, dou psi by dou z is equal to Vx we can write total differential of phi total differential of psi xz as d psi is equal to minus Vz dx plus Vx dz. So, for a given flow line, if psi is constant, d psi is equal to 0. For a given flow line, if psi is constant, then d psi is equal to 0. So, equating this equation what we deduced for total differential of the psi xz to 0, we will get d psi is equal to 0 is equal to minus Vz dx plus Vx dz. So, with that what we get is that the slope of the stream function dz by dx is equal to dz by dx of psi, that is the stream function, is equal to Vz by Vx. Now, we can see that this is the stream function, streamline or flow line. So, Vx is the velocity in x direction and then Vz is the velocity in the z direction. So, with this what we can say that if you note down the dz by dx of phi is what we obtained as minus Vx by Vz, and dz by dx of psi we obtained as Vz by Vx. So, they are it appears that they are orthogonal. So, with this deliberation it is apparent that the flow lines and equipotential lines are intersect at right angles to each other. So, from the deliberation whatever we have deduced from the theoretical considerations, we can say that the flow lines and equipotential lines intersect each other orthogonally. So, here in this slide which is shown here, this is a streamline which is shown here, and delta B is the difference between distance between two streamlines or flow lines. The distance between any two flow lines we described as flow channel. So, this is the flow channel which is indicated. Delta Q is the small flow occurring through this flow channel, and delta L is the distance, that is the length over which the flow is taking place, that is the distance between any two equipotential lines. So, if you consider here this is equipotential line and this is equipotential line. So, the total head along these 2 points is 0. So, if I consider a total head at this point, it will be somewhere here with respect to certain datum. So, similarly, if I take an equipotential line, that is if I tap and measure the total head here. So, what we get is also same total head, that indicates that total head is constant along this. But if you consider come down here, so because the flow is taking place, so that particular the energy is transferred in the form of a frictional drag to the soil grains. So, in the form when the flow is taking place to soil, the head loss has to occur. So, here the drop which is taking place for a distance that is delta L to flow to take place is around delta H. So, if you can also say that the hydraulic gradient is now delta H by delta L. For steady state seepage conditions, the I is equal to constant. So, here if you see this is the total head for this equipotential line, and this is another equipotential line which is there and which is having a loss, which because it experienced a loss, that is the total head is less than delta H. That means that delta H is the head loss which is taken place between these two equipotential lines. So, if you note down here from the theoretical deliberation, so if you see that the angles where they meet both flow lines and equipotential lines, they are orthogonal. So, this particular aspect orthogonality of flow lines and equipotential lines have to be kept in mind while constructing flow nets. So, that we will be using that concept, and then we will be considering the different types of structures with confined seepage conditions and unconfined seepage conditions. Confined seepage conditions are basically with sheet pile walls or a masonry structure embedded in a permeable soil medium, and in case of unconfined seepage conditions, a flow through an earth dam can be considered as a unconfined seepage conditions. So, in these two considerations when you take, and what we can get is that we can estimate the flow which is taking place through an entire medium, then we can estimate the total discharge. So, and also with this we can also determine another benefits like the safety against some uplift and safety against some piping, and these aspects can be considered into this. So, based on that, with this we will be able to design and arrive at the remedial measures. So, Now, this having derived these potential functions and stream functions, let us try to apply this continuity equation for the solution of simple pro problems. So, let us assume that we have got a container having LA plus LB, total length as L is equal to LA plus LB, and two soils are filled in this container. Soil A is having a length LA. So, it between 1 to 2 points the soil A is there, from 2 to 3 points soil B is there. So, let us assume that it is assumed in a frictionless medium, and then the flow is taking place in one direction, that is the x direction is here which is defined and z direction is here. So, the flow which is actually taking place confined between two this container walls, the flow is taking place along the x direction. So, this is one dimensional consideration. So, here if you consider at point 1 the total head is H1, at point 2 that total head is H2, which is to be determined, and here already head loss has occurred. That means that the entire, if you look into it, the total head loss is which is driving the flow from 1 to 3 is around total head which is driving the flow is around H1. So, this one dimensional flow through two layers of soil, and after having deduced an expression for two layers of soil, we can apply easily for one dimensional flow through a single layer soil. So, H1 is greater than H2, that is actually required to be noted, because naturally when the flow is taking place, so the head loss will occur, so the H2 will be less than H1. So, use of continuity equation for solution of simple flow problems. So, one dimensional flow through two layers of soil. The flow is in one direction only because it is an x axis, that is x axis. The lengths of the two soil layers LA and LB, and their coefficients of permeability in the direction of x axis are known. That is, lengths are known, and coefficient of permeabilities, Darcy's coefficient of permeabilities Ka and Kb are known to us. And total heads at section 1 and 3 are known. That means that we do not know the H2 in between, but we can determine by using the this particular deliberations which we are going to discuss, but head at 1, total head at 1 and total head at 3.3, which is shown in the figure in the previous slide, can be noted. So, total head at section 1 and 3 gives which is known to us. So, required now is total head at any other section for distance between 0 and LA plus LB. So, let us consider for one dimensional flow through two layers of soil, the integration of the Laplace equation in one dimensional flow consideration, that is dou square H by dou x square is equal to 0, because that is the equation for Laplace equation of continuity for one dimensional flow. So, with that we can say that by integration of that we will get H is equal to C2x plus C1, where C1 and C2 are constant. X is the distance along the x axis. So, for the flow through soil A, the boundary conditions if you wanted to dictate, then at x is equal to 0, H is equal to H1. That is, when the x is equal to 0 at point 1, x is equal to 0, H is equal to H1, the total head is H1, that is the commencement of the flow is taking place at point 1. And at x is equal to LA, H is equal to H2, that is H2 which is unknown, but the H is equal to H2. So, by solving now, substituting in H is equal to C2x, H2 is equal to C2x plus C1 for x is equal to 0, then we can say that C1 is equal to H. Similarly, substituting for H is equal to H2 and x is equal to LA, and solving and simplifying, we will get H is equal to minus of H1 minus H2 by LA into x plus H1. So, H is equal to which is valid for distance between 0 and LA, that is which is valid for 0 and LA. We are not gone to the soil B, we are still in the soil A, which is having a length completely LA. So, with this what we can determine is that the head at any point we can determine in terms of say H1, H2, LA, X and H1. Now, when similarly when we consider now the flow which is taking place from point 2 to 3, that is in the region of the soil B. So, in the previous slide we have shown a figure having 2 points, the 2 and 3, that is which is shown again here. So, this is soil B, which is flow taking place between 2 and 3, that is LB. So, let us now consider the boundary conditions. Again the flow is taking place in one dimensional direction. So, that del square h by dou x square is equal to 0, and integrating we get h is equal to C2x plus C1. For flow through soil B, the boundary conditions are at x is equal to LA, h is equal to H2. So, at the commencement of the at the end of the x is equal to LA, the head is h is equal to H2, and x is equal to LA plus LB, that is the entire that is from left hand side to right hand side, that h is equal to H0. So, now we substituting this and solving for boundary conditions, then we will get for x ranging from LA to LA plus LAB, LA to LA plus LB, we get h is equal to minus H2 by LB x plus H2 into 1 plus LA by LB. So, this is from the region flow through soil B. So, this is valid from distance LA to LA plus LB, that is the right hand side end of the container end which we are under consideration. So, now let us consider Q is the rate of the flow of the soil through area of cross section A. Area is perpendicular to the A is now which is perpendicular, that is x along the length, and perpendicular to the plane of the figure if the unit is 1. So, that is cross section is indicated, area of cross section is indicated as A. The rate of flow through soil B is equal to rate of flow through soil A, that is has to happen. So, Q is equal to Ka into H1 minus H2 by LA into A is equal to KB into H2 by LB into A. So, because at point 2 the head which is available is H2, at point 1 head available is H1. So, what we have H1 and H2, which is the head which is the total loss which is occurring between point 1 and 2 is H1 minus H2. So, the hydraulic gradient in this case is H1 minus H2 by LA, and Ka is the coefficient of permeability for soil A in the x direction, and A is the area of cross section. Similarly, Kb is the coefficient of permeability of the soil for the soil in the x direction for soil B, and H2 is the head which is occurring, the loss which is taking place from point 2 to point 3. So, H2 by LB, LB is the length of the soil B, and area A is the area of the cross section. So, A is the area of the cross section of soil perpendicular to the direction of flow. So, by solving this and substituting in the previous expression, we get H2 is equal to, so this by solving, equating these two and solving, we get Ka H1 divided by LA into Ka by LA plus Kb by LB. With this now, if you simplify and substitute in the previous expression what we derived, then we get one dimensional flow through two layers of soils. We get for x is equal to 0 to LA, we get expression like h is equal to H1 into 1 minus KBX by Ka LB plus Kb LA. Similarly, for x is equal to LA to x is equal to LA plus LB, that is h is equal to H1 into Ka by Ka LB plus Kb LA into LA plus LB minus x. So, for if you consider that now this is an expression for two layers of soils, two soil layers, that is two soil types A and B having lengths LA and LB placed in a container having a cross section area A, where the flow is occurring from point 1 to point 3. So, we try to determine by using the continuity equation the head at any point. So, that same concept can be applied, because we have discussed it in the beginning, like when the flow is taking place over a length L, say let us assume that the same container of LA and LB, the length is say L, and if it is having a one type of soil, then LA is equal to LB is equal to L, and Ka is equal to Kb is equal to K. So, for that if you look into it, say for that is at x is equal to L by 2, that is x is equal to 0, that is h is equal to H1, the total head is remaining there, because the no loss has taken place, because the flow is about to commence. At x is equal to L, that is at the end of the once the flow has taken place, that is the point where the flow has already taken place, that is the length of the flow. At the end of the length of the flow, that is x is equal to L, then in that case h is equal to H1 into 1 minus 0, that is 1 minus 1, that is 0. So, it tends to be total head available is 0 for the flow to take place. That means that the flow has already taken place, the total head has already been reduced to 0. So, for say at in between points, say x is equal to L by 2. So, we can determine by using this expression h is equal to h1 into 1 minus x by L. So, this is reduced by substituting in these expressions and then we got this expression h is equal to h1 into 1 minus x by L. So, if you say that x is equal to L by 2, that is that once the flow is 50% length of the flow, then we can say that the total head is already lost is 50%. That means that from h1 is reduced to around h1 by 2. Similarly, if you wanted to say at 1/4 distance, that is the head is again 25% of the head loss will occur. Say 3/4 distance of the length L, then 75% of the head loss would have occurred. At the end of the length of flow, 100% head loss would have taken place. So, that is what what we discuss, and then we used the continuity equation to deduce these expressions. Before explaining these problems relating to flow net construction and then the methodologies for the flow net construction, we should also try to remember the pore pressure variation in a steady state seepage conditions. So, in case of a steady state seepage conditions, the hydraulic gradient is constant. So, consider in a medium say a permeable medium where the flow is taking place, P and Q is a flow line where the flow is taking place in this direction. Assume that this is a potential line here and a potential line which is approximately drawn, which is orthogonal here, and delta S is the length of the flow line over which the flow is taking place. So, delta H is the head loss which is taking place, or the drop which is occurred between potential lines passing through point P and Q. So, that is delta H by delta S, which is nothing but a hydraulic gradient. So, here we can say that for steady state seepage conditions, I is equal to constant. So, change in pore water pressure between any between 2 points P and Q, the per unit width we can write as delta U is equal to I gamma W into delta S into 1, that is perimeter length of the cross section is say 1. Then we can say that the change in pore water pressure, the small change in pore water pressure delta U is equal to I, which is the hydraulic gradient which is constant. Then gamma W is the unit weight of water, and then delta S is the distance between these two flow lines. So, pore pressure in the steady state flow conditions which is defined here. So, when the water flows through a porous medium such as soil, head is lost through friction. So, if you recollect again, when water flows through a soil medium or a porous medium, head is lost through friction. So, similar head losses occur when water seeps through a net dam. That is example for net dam, we discussed that unconfined flow conditions, or example for unconfined flow we can say that net dam. And under a sheet pile coffer dam or a concrete masonry dam, the confined flow conditions can come. Sheet pile coffer dam or concrete masonry dam, the confined flow conditions can be provided. So, as the particle of water proceeds from A to B, so A to B are the 2 points over which the flow is taking place with some potential difference, then it exerts a frictional drag on soil particles, and this drag in turn produces seepage pressure in the soil structure. So, this seepage force always acts in the direction of a seepage pressure always acts in the direction of a flow line, in the direction of flow, that is along the flow lines. So, as the particle of water proceeds from A to B, it exerts a frictional drag on soil particles. So, this drag in turn produces seepage pressure in the soil structure. So, let us try to consider and apply this knowledge on flow nets to constructing the flow net construction. So, here as is indicated, a confined flow condition, which is the sheet pile wall problem, is shown here. So, let us assume that we are having a line of sheet pile walls which are driven into a soil to maintain upstream water levels and the difference between upstream water level and downstream water level. And if particularly this sheet pile wall which is driven into the ground and which is perpendicular to the plane of the figure, the length is continuous, and if the flow is taking place, then the flow takes place from higher head to lower head. So, in this case now here upstream water level and downstream water level are the one. That is the difference between upstream water level and downstream water level. Here the head loss which is difference between upstream water level and downstream water level is somewhere around here